Yeah, so thank you very much for attending and for the opportunity you're giving me to present. So this is a work that I've done in my PhD thesis with my advisors, Antonio Chambol and Vincent Duval. And so let's go. So what is the problem that we want to solve? It's a variational problem. And well, given a compacted convex subset of RD, we give also ourselves a probability measure. We want just to solve this variational problem, which consists in a data term that is given by the Wasserstein 2 distance, which is defined like this, which is a metric over the space of probability measures, which metrises weak convergence. We've seen this a couple of times in this conference. And in addition, we have a regularization term, which is the total variation functional, defined here as here for some measure rho as the soup of the integration of the divergence of all the vector fields Z, which are smooth, and so on and so forth. The take-home message of this functional is that if our probability measure is C1, then we're just taking the L1 distance, the L1 norm of the gradient. Okay. So talking a little bit more about our data function, data term, and the regularization term, the Wasserstein distance, I'm sure we all know, is defined through the value of the optimum transportation problem, right? Which, given a marginal mu, we want to transport it to minimize the total transportation cost of transportation into nu. And this we do by minimizing this quantity here. The squared Euclidean distance here is interpreted as a punctual transportation cost. And we integrate over couplings, not in the sense that Magali just told us, but in the sense that it's just a probability measure with these marginals. And of course, we also have the Kantorovich duality, which is meaning that this minimization equals to the soup. This is the dual problem in the sense of convex analysis. It's the soup among all the continuous and bounded functions phi and psi, satisfying this bound. And we minimize this quantity, which is interesting because we actually decoupled the dependence on both measures. Now, a little bit about the total variation. It was mostly introduced for applications in imaging, for example, for denoising. For instance, for the problem that is known nowadays as the Hopf problem, which stands for Houdin-Urschel-Fatemi, consisting of minimizing on very similar minimization problem, but this is much more classical, which is this very similar variational problem with the same total variation regularization, but now we are using a L2 norm as a data term. Okay? So this is very classical, and by now we understand this problem very well. And one thing that we understand about it is when we iterate it. What I mean by this is that, well, we give ourselves an initial condition, just like we said at the row 0 here, think of U0. We use this as a data term. We solve this problem, okay, and obtain some, let's say, U1. And then this U1 we plug it back again, obtain a U2, and so on and so forth. So we obtain a sequence like this. Then we glue the sequence together as a staircase interpolation. So now we have a continuous time evolution, let's say. And we take, well, of course, we're going to take the optimality conditions of this optimization here, of this minimization problem here, right? So since we have a convex and lower semi-continuous function plus a smooth function, the optimality conditions are just going to be in the form of Fermat's rule. 0 becomes in this differential of the sum, which is the sum of the subdifferentials in this case. And when we take now lambda here, we make it go to 0, what we actually obtain is a nice PDE thing. It's actually a differential inclusion, but we obtain a nice evolution equation here. Yeah, which was not hard at all to obtain. The question is now, okay, so what happens if instead of using the O2 geometry, you use the Wasserstein one? Okay, and there is a huge literature about this, but not so much for the total variation. The conjecture, which has been proven in 1D under some technical assumptions on the initial measure, is that it converges to a differential inclusion like this. Okay, so for those who know a little bit of JKO, we were going to recognize a auto gradient here, auto calculus thing. Okay, so how do we prove convergence in general for this? It's more or less the same thing that I just said. We start solving, we obtain the sequence that I described by solving the sequence of variational problems. We glue everything together. We use some compactness to pass to the limit and obtain a continuous process in some evolution equation. And then we have to somehow characterize the evolution to say which PDE it's actually solving. And we describe this precisely with the optimality condition. So the key thing here is how we obtain it and how much regularity we extract from this, right? From the optimality conditions. And this was initially done in a paper by Guillaume Carlier and Clarice Poon. And they used a entropic regularization approach of the Wasserstein distance plus a gamma convergence argument. And this is very long, very complicated, and gives less information. And what we propose to do in this work is to derive the same optimality conditions, now making the link with the well-understood Hoff problem. And in the process, we actually obtain more regularity and obtain more information with less complicated proofs. So, which is always nice, for at least for me. So the result that we obtain is this. Here, rho 0 is the measure that we already given ourselves. Rho 1 is the minimizer of our problem. And then the optimality condition states that there exists a vector field Z, which is in H10 div, L2 function with whose divergence is in L2. And the Lagrange multiplier beta, which is non-negative and is associated actually with the non-negativity constraints of the probability measure, right? It's a bit hidden, but that's where it comes from, actually. And these quantities, they are related through this equation where psi, if you remember, is the psi from the dual formulation of the Wasserstein distance associated with the solution. We call these things, these maximizers, Kontorovich potentials. So it satisfies this relation. Then we have complementary slackness from the non-negativity constraints. And finally, Z is special because it's some sort of phase of the derivative of the solution, in the sense that when we multiply it with the gradient, we get the norm of the gradient. Okay, this actually is the condition that states that div Z belongs in the subdifferential. So this is more or less what was proved in this Stanley, just a bit different way. Yeah.
Sorry, what's tau?
Tau is the parameter that we had in the beginning. It's the time parameter, right? So we make this go to 0 in the limit, but we're not going to be worried about this. Just because the focus is to derive the optimality conditions, not to pass the limit yet. Yeah, so this is what more or less was derived by Guillaume Carlier and Clarice Poon. What we are able to say more with our approach is that actually the Lagrange multiplier beta here, it also solves a Hoff problem with a different data function, okay? And all these functions here, they are Lipschitz, which is actually important because when to pass to the limit, we actually have to take the gradients of all these things here. We didn't know this before, so it was a little bit of cheating, but we do it anyways. So yes, now we can. So I would just give an idea, a sketch of the idea of the proof. So we take here rho 1 to be a minimizer of our problem. We show then that there is some Kontorovich potential. That can be more than one, okay? But there is one, such that rho 1 also minimizes this energy here, okay? We're able to show this. Then we define another magic function here that I call it G on purpose because I want it to be the data term of another Hopf problem. And I will just add this L2 regularization for this previous problem here. Okay? I take the solutions of this guy. I have the right to do this. And it turns out that this problem is just another instantiation of the Hopf problem with this new G. Okay, you just have to do some computation and we'll verify this. Then what I do is I compare the energies of the positive part of this guy and of the solution, rho 1. So I get two inequalities here. And when I sum them, there's the infamous, with a little bit of algebra, we get this inequality, which means that they're the same function. So the solution of my variational problem is the positive part of this new one. Okay. So why is it important? So a little scheme, because I think it's easy. It's easier to visualize proofs like this. So I take a minimization, a minimizer. I define the function that I said before, and I compute the solution of the Hopf problem. So as we said before, the Euler Lagrange equations for the Hopf problem, they're actually easy, and it's assumed this form. Okay? But then here's the catch. Because from a result of the total variation, which I call the core-area formula, it holds that you can say this lemma that nobody reads the proof. The subdifferential of the total variation of some measure or function is contained on the subdifferential of its positive or negative parts. But I know what the positive and negative, what is the positive part of UT. It's rho 1 that we just proved. So this quantity actually belongs in this subdifferential of rho 1. And now we use the characterization of the subdifferential. That's where the div z's comes from. These subdifferentials, they are actually the divergence of these vector fields. They're precisely the ones that are stated in the theorem. And so this thing actually writes like this when we substitute the G here with this guy. But what's slapped here is actually the positive part of a function minus this function. So it's minus the negative part. Sorry, it's the negative part, which I call the beta. So there beta is positive. And since it also belongs in the subdifferential of the negative part, so beta, I actually get the Euler Lagrange equation of beta of another problem. So that's the little improvement. Okay, so after this potentially tedious proof, some numerics. Well, we proposed an algorithm to solve this, right? There were some algorithms in the literature that were based on the fact that we already knew that the limit was that PDE. So basically, people solved the time step of the PDE, which is not proven yet. So it's nice to have another alternative. And it's based on a Douglas-Rashford iteration for a minimization of a sum of convex functions. Okay. So in our case, the f and g here, they are the total variation, of course, and the squared Wasserstein distance. So the Douglas-Rashford algorithm is a proximal splitting algorithm in the sense that what we do is we minimize first one function of this prox operator that I'm going to define, and then we minimize the other function, and we reiterate these alternative minimizations. And well, the prox operator that I just said here is defined as the minimization of the function plus another L2 regularization that we're doing a lot. For the TV, it's exactly a Hopf problem. So there is a huge literature for this, and with very fast codes. For the Wasserstein distance, it actually writes, again with a little bit of algebra, it writes like this, which is one step of the gradient flow of another PDE, the Paris-Minion PDE. So just to say that there is also a huge literature about this, and people have done a lot of work to solve this numerically. So I just got the two procs for free. Other smart people implemented this for me. And also that we have an algorithm, some numerical experiments. The first one is to kind of validate that this method works. So we proved that if the initial condition is a little ball of radius r0, then this solution is also a ball of radius now of r1, solving a polynomial equation, depending on r0, of course. On r0, the dimension and the time step that we're using. So here in this picture, we see the initial condition, the initial little ball, and the evolutions, and the red circle around them is the theoretical radius that we would expect. So we actually see that the results of the algorithm are actually very reliable, and they are reliable approximations of the theoretical results that we expected. There is also one thing to notice here, that actually with a little bit bigger time, we get a better approximation than with a smaller one, which is to be expected, because if this tau here is too small, then things explode and it's not so good. The other application, well, I wouldn't say application, experiment, is in the reconstruction of quantized images. So here is an image that I already passed from some quantization process, meaning that it's just, this image here is just of zeros and ones. And we expect to use our variational problem to reconstruct what would be the image that we got before this quantization problem, this quantization process, right? Here on the far right is actually what we obtain from the Hopf reconstruction, which already looks kind of nice, but there is a problem that we still have a pixelated behavior. There is still regions that we see like a sharp change of gray level, whereas with the Total Variation Wasserstein reconstruction, we also get some complex textures, but with a smoother behavior without, let's say, direct masses, right? And this is actually very natural to expect, because the L2 topology does not metrizes conversions of measures, whereas the Wasserstein does, and the direct masses are exactly the extreme points of weak convergence, right? So just to conclude, in this work we have re-derived Euler Lagrange equations for the Total Variation Wasserstein problem. We got an interesting theoretical relation with the Hopf problem that is very important in the mathematical imaging literature, and we also got a better regularity for the results for the quantities involved. In addition, we also proposed a numerical algorithm to solve our problem, which was consistent with theoretical predictions, which is always nice. And we used it to reconstruction of quantized images. So with this, I thank you for your attention, and I'll be happy to answer any question.
Questions? Remarks? I'm still a bit puzzled with the tau. So you always consider, make me a little bit nervous. The tau is always quite big, right, in your simulation?
No, it's meant to be, I mean, it's not so big. It's 0.5, 0.1, 0.2.
Okay, because
yeah.
things look like they are going to explode.
Sorry?
Because some terms look like they are going to explode with a little tau, no?
Yeah, that's for sure. You mean here?
Yeah, definitely there.
Yeah. Yeah, they would explode. The thing is that when we want to pass the limit, I said we take the gradient here, right?
Right.
And the gradient of this guy is actually, although it's a bit technical in optimal transport, but the gradient of this guy is the optimal transportation map minus the identity. And the idea is that if I am evolving just a little bit, the marginals are closed, so I transport just a little bit.
Okay.
So I transport, the transportation is in the order of tau, more or less.
Okay.
So actually, okay, here in this equation it would explode. But when I take the gradient, it's some sort of velocity. Because it's the transportation, the transported minus the initial, so it's final minus the initial, over delta x over delta t, you get some sort of velocity interpretation. It's a bit technical on the what comes later.
Yeah. Okay, thanks.
Yeah.
Any more remarks or questions? Okay, so let's thank the speakers.